Integral, the International Gamma Ray Astrophysics Laboratory, will carry the heaviest payload ever sent into orbit by ESA. On top of the service module, which uses the successful design of the XMM Newton telescope, are 2 tons of instruments designed to work in concert with each other. The IBIS imager will detect the positions of gamma-ray sources and create the most detailed maps yet of the gamma-ray sky. Integral's elliptical orbit will allow the instruments to work for 3 days at a time, switching the detectors off for 6 hours in every orbit to avoid the blinding effect of the Van Allen belt during perigee passage. 100 times more sensitive than previous instruments, the SPI spectrometer will record the colour and intensity of the gamma rays. It will also have the task of determining what kind of sources emitted them. 3 meters above the instrument platform are the coded masks. These metal masks function on the same principle as a pinhole camera and will produce the images of gamma-ray sources on the detector planes. Together with an X-ray monitor and a co-aligned optical camera, these instruments will enable scientists to see invisible gamma rays in unprecedented detail, which will in turn enable them to correlate optical, X-ray and gamma-ray sources in the sky. Integral will enable scientists to explore the most elusive, yet potentially revealing part of the spectrum, invisible to the human eye. Powerful telescopes in space already look at X-rays or infrared radiation, but gamma rays have so far remained one of the most difficult tasks. 5 million times more energetic than visible light, they pass through matter with hardly any interaction. Gamma rays are highly energetic light particles, created by dramatic events such as the supernova explosions which mark the death of stars, by neutron stars and black holes. Scientists believe that the heavier chemical elements such as gold and iron originated in supernovae. Integral will enable them to look for the signature of these elements in the nebulous surroundings of distant supernovae. By examining gamma rays from the vicinity of stellar objects such as neutron stars and black holes, we can try and understand these elusive objects better than ever before. Integral might even shed light on the question of what is at the centre of our own galaxy. From close, compact objects to huge forms hovering on the edge of space and time, Integral will offer a new vision of the universe. During a mission which will last up to 5 years, Integral will catalogue all the gamma-ray sources in the sky, finally enabling scientists to test theoretical projections against material data. In this way, it will provide the key to a previously unexplored world, and no one can predict exactly what this mission might uncover. Integral's first few days in orbit are taken up with the task of reaching the best orbit to make observations of gamma rays. Integral moves in an elliptical orbit, and the first 3 stages of proton burn achieve an apogee, or furthest point, of around 690 kilometers from Earth, and a perigee, or closest point, of about 190 kilometers. This initial low Earth orbit is maintained for about 50 minutes before the 4th stage of the proton ignites, lifting Integral towards what will be its operational orbit. The apogee now climbs to 153,000 kilometers with a perigee of 690 kilometers, a feat which uses up all of the fuel on the proton. 20 minutes later, Integral separates from the proton and its solar panels open. At this point, the telescope's mission has officially begun. Each revolution in Integral's operational orbit takes around 72 hours. During the first and second revolutions, spacecraft subsystems such as star trackers and reaction wheels are switched on and checked. From the third to fifth revolutions, Integral uses its own motors to raise the perigee height to 9,000 kilometers, consuming just over half of the 540 kilograms of fuel carried on board. The next 8 weeks are spent fine-tuning and adjusting the parameters of Integral's instruments to maximize their scientific performance. With these tasks complete, by mid-December 2002, Integral will be ready to start gathering data. Every day, a spectacular flash takes place in the sky above our heads. Completely invisible to the naked eye, it is the most violent event in the universe as we know it, a gamma-ray burst. No one knows where gamma-ray bursts come from or when they will happen next. They could be the products of extremely violent explosions from the distant reaches of the universe. If so, the light they produce will have travelled through space for billions of years, carrying information about the earliest conditions in the universe. Or, gamma-ray bursts could represent an entirely new kind of stellar object near the edge of the observable universe. If so, they could be a new observable tool for cosmologists. Either way, scientists want to find out more about this mysterious phenomenon. But although a gamma-ray burst outshines all other sources of cosmic gamma radiation added together, the source of the burst disappears after only a few seconds. Today, it takes scientists days to identify the exact location of a gamma-ray burst. During this time, crucial data on the afterglow of the burst is lost. The Joint European X-ray Monitor, GEMX, will allow astronomers to immediately monitor this afterglow of lower energy X-rays, which can be seen much longer than the burst itself. Earthbound telescopes around the world will receive instant notice that a gamma-ray burst has occurred through the Integral Science Data Center at the Geneva Observatory. They will be able to start making observations in the visible light immediately. In this way, Integral will take the first step towards unraveling the gamma-ray enigma.